Okay, good morning, student. I am Shivraj Singh, Assistant Professor in Electronics and Communication Engineering branch. Today, I will discuss about the network theorem. Right? Network theorem basically used for simplification for a complicated circuit. In circuit, maybe dependent source, independent source, like this. So here we will be discuss about different. There are different type of networks theorem, like Thevenin's theorem, Norton's theorem, maximum power theorem, superposition theorem, reciprocity theorem, intelligence theorem. These are the different types of network theorem. But today I will discuss about Thevenin's as well as Norton's theorem. First, we will be discuss about the Thevenin's theorem. Thevenin's theorem, according to Thevenin's theorem, any linear active bilateral complicated network across its load terminal can be replaced by a single voltage source along with a series arm impedance. If if the circuit have if the circuit have only resistive network, then we consider as a DC source. And in the circuit have inductor, capacitor, resistor, then we consider as a AC source. So we will discuss about network theorem. So here, according to this theorem, firstly we uh, seen here this is a uh, this is a upper network, ठीक है, across this A and B is the load terminal. Suppose that here we connect a load terminal, so this complicated network across this load terminal can be replaced by a single voltage source along with the series impedance, right? And the last, here the terminal A and B, we connect the load terminal, that is ZL, and we can find out the response across the load, maybe voltage, current, power, energy, etc. Here we can see this circuit. This circuit represents the Thevenin's equivalent circuit, where VTH, that is called as Thevenin's equivalent voltage source, या open circuited voltage source. Why? Because VTH measured in the open circuit. ZTH is the Thevenin's equivalent impedance. Right? At the end, we can calculate the load impedance. So here we connect the load terminal in the Thevenin's equivalent circuit, that is VTH, ZTH, and ZL. We connect the load in the series. Okay. So again, here the load IL equal to load current is given by IL equal to VTH upon ZTH plus ZL. Now, how can measure the VTH and ZTH from this circuit? So here we follow these steps to calculate the response. Firstly, remove the load terminal. First, first we remove the load terminal. Then calculate the second step. Then we calculate the VTH. VTH calculated uh, across the load terminal. For this, we can remove the load terminal and we can measure the VTH in the open circuit. Again, we can third step is we can calculate the Z equivalent. For this, we can replace the source with respect to their internal resistance. If circuit have a voltage source, then voltage source replaced by a short circuit, and current source replaced by a open circuit. Again, at the end, we can draw the Thevenin's equivalent circuit along with the load impedance, and then calculate the load current IL. Suppose that here we consider a circuit, complicated circuit, VTH, Z1, Z2, Z3, and this one is the load impedance. Across this load impedance, we can find out the response like IL, VL, or load voltage or power. So firstly, we remove the load terminal and then calculate the VTS. So VTS measured in the open loop. Here, firstly remove VTH calculated by in this circuit we can see that the voltage drop across Z3 will be 0 because this circuit is open. So according to voltage division rule, the voltage across Z2, the voltage across Z2 must be equal to VTH, and then VTH according to voltage division rule, VTH equal to source voltage, this one, into Z2 upon Z1 plus Z2. Again, we calculate the Thevenin's equivalent impedance, that is ZTH. For this calculation of Thevenin's equivalent impedance, firstly we replace the source with respect to their internal resistance. So here the voltage source is replaced by a short circuit and measure the ZTH. So ZTH must be equal to, that is Z1 and Z2 is the parallel combination and Z3 is the series combination. So here ZTH must be equal to parallel combination of Z1 and Z2, that is Z2 upon Z1 plus Z2, and Z3 in the series combination. Again, draw the third step, draw the equivalent circuit. The after calculation of VTH and ZTH, we can draw the Thevenin's equivalent circuit. So here this VTH and ZTH are connected in a series. Now at the last we find the response, that means load current. For calculation of load current, we connect the load impedance at the load terminal. That means we connect this load at the point A and B terminal. Now this series combination VTH, ZTH and ZL, we can calculate the load current. Load current, here the load current IL equal to VTH upon ZTH and ZL. That is response या current across the load terminal. Again, we will discuss about the Norton's theorem. According to Norton's theorem, any linear, active, bilateral complicated network across its load terminal can be replaced by a single current source along with a parallel impedance. So here we can see the a complicated network, or A or B are the load terminal. So across the load terminal, this complicated network can be replaced by a single current source IN, that is called Norton current source, and parallel combination of ZN, that is called Norton's equivalent impedance. And at the last, we connect the load terminal, that means in parallel of Norton equivalent circuit, and find the response of the circuit. That means we can find out the current or voltage or power across the load terminal Zn. So here, sorry, IN, load current IN. So according to, in this circuit, according to current division rule, according to current division rule, we can calculate the load current. That is, load current IL must be equal to the source current IN into opposite arm impedance Zn upon Zn plus Zl. That is the load current across the load terminal Zn. So how can calculate the response, that is load current or voltage current or power? So here we follow the different steps. Firstly, remove the load terminal and measure the Norton's current. For this we can Norton current. Again, we can calculate the load. We can calculate the Norton's equivalent impedance. It's just like a Thevenin's equivalent impedance, right? That means Thevenin's equivalent impedance and Norton equivalent impedance are same. And at the last, we can calculate the load current. So here, same example. Suppose that, consider this circuit. Here voltage source Z1, Z2, Z3, and this is the load. Here we can find out the response across this load terminal. That means we can find out the load current. So here, firstly remove this load terminal Z1 and replace by a short circuit. And here we can measure the Norton's equivalent current. So here in this circuit, firstly we can solve any method by using current division rule or loop analysis method or node analysis method, like this one. So here, suppose that, assume that the I current flow through this supply. So here the current I must be equal to the voltage upon total impedance. Here Z2 and Z3 is the parallel combination and Z1 is the series combination. So here we can find the current I must be equal to voltage upon Z1, that is series combination, plus Z2 and Z3 are parallel combination. So here Z2 Z3 upon Z2 plus Z3. If we can calculate the I, then according to current division rule, we can find the Norton current. That is IN equal to total source current I into opposite arm resistance Z2 upon Z2 plus Z3. Here, that means we can calculate the Norton's equivalent current source. Again, second step, calculate the Norton's equivalent impedance. We can follow the same procedure just like a Thevenin's theorem. So here the source, maybe voltage source or current source, replaced by their internal resistance. If have the voltage source, that means replaced by a short circuit, and the current source replaced by a open circuit. So in this circuit, here voltage source may be replaced by a short circuit, and then measure the Norton's equivalent impedance. So here Z1 and Z2 is the parallel combination and Z3 is the series combination. So here total Zn equal to Z1 Z2 upon Z1 plus Z2 plus overall Z3 is the addition of this parallel combination. At the last we can find out the load current. So here IN and Zn is the parallel combination, that is Norton equivalent circuit, and across this load, the load are connected in this point, and we can measure the load current. So according to this circuit, the the load current measured with the help of current division rule. So according to current division rule, the load current IL must be equal to the total source current, that is IN, and across opposite arm impedance Zn upon Zn plus Zl, that is the load current. Now this theorem, uh, by using this theorem, we can solve some problems. Here, first one, in this circuit, find the current passing through the 4 ohm resistor like this one. We can find the response here, load current, with the help of Thevenin's as well as Norton's theorem. So firstly, we apply the Thevenin's theorem. In this circuit, we can show here the voltage source 5 ohm, 1 ohm resistor, 3 ohm resistor, 2 ohm, and the 4 ohm is the load. So by using Thevenin's theorem, first we calculate the VTH, that is Thevenin's equivalent voltage. For this, firstly remove the load terminal. That means we can remove the 4 ohm resistor, and at this point we can measure the VTS. So VTS, here we can see this is the positive terminal, this one is the negative terminal. Again, in the open loop circuit, current must be equal to 0. So the voltage across 2 ohm resistor must be equal to 0. That is, the voltage across 3 ohm resistor must be equal to VTH. So here we can measure the VTH equal to the voltage drop across 3 ohm resistor. So according to voltage division rule, the voltage division rule, here the VTH must be equal to total source voltage V in V, that is 5 into 3 divided by 1 plus 3, that is overall VTH equal to 3.75 volt. Again, second step, calculate the Thevenin's equivalent impedance. So for this, we we can replace the source with respect to their internal resistance. Then here we can replace the voltage source by a short circuit and then measure the ZTS. So here the Z1 and Z2 is the parallel combination. Parallel combination. Here Z1 and Z1 and 3 ohm resistor is the parallel combination, and 2 ohm is the series. So that is ZTH equal to 1 into 3 divided by 1 plus 3 and plus 2, that is 2.75. Again, at the last, we calculate the load current. For this, we can connect the load terminal ZL, that is 4 ohm, and then measure the load current IL. That is IL equal to VTH upon RTH plus RL. So here VTH must be equal to 3.75 ohm upon RTH equal to 2.75 plus 4 ohm. That means overall 0.5. Again, same circuit we can solve with the help of Norton's theorem. The same response are find uh, here. Sorry, here by using Norton's theorem, Firstly, remove the load terminal and replace by a short circuit and then measure the IO. So here we can assume the current I. Okay? I is the source current flow through this source 5 volt. So here we can measure the I. So here 2 and 3 ohm resistor are parallel combination and one is the series combination. Then here we can calculate the current I equal to 5 upon 1 plus parallel combination of 3 and 2. That is 3 cross 2 upon 5. That is overall current 2.1 2.27 ampere. Again, with the help of current division rule, we can find out the Norton's current. Norton current must be equal to total current I, that is 2.27 ampere, into opposite of the resistance, that means 3 ohm upon 2 plus 3, that is 1.86 ampere. Again, we can calculate the Norton's equivalent impedance. So same procedure follow as a Thevenin's theorem. So here we can replace the voltage source by a short circuit. That is Zn is the parallel combination of Zn, 1 and 3 is the parallel combination and 2 is the series combination. That is Zn equal to 1 cross 3 upon 4 plus 2, 2.75 ohm. Again, the load current, again we can at the end we can find the load current. So here we can connect the load terminal in the Norton equivalent circuit. So here the current 1.36 ampere and 2.75 ohm is the parallel combination. Across this we can we can connect the 4 ohm resistor and then calculate the load current. So according to current division rule, we can find out the load current, that is total source current I equal to 3.16, resistance 2.75 upon 2.75 plus 4, that is 0.55. This is the same as the Thevenin's theorem. Okay, thank you, class.